The moon is close. Close enough to see tonight with your own eyes. Close enough that a rescue ship could reach a stranded crew in days, not years. And that nearness is exactly what makes the real danger so easy to miss. Landing on the moon was never the hardest part. Neither is building a base. The horrifying problem begins when humans try to stay for good, through equipment failures, delayed supply ships, and emergencies that Earth cannot reach in time. Every breath, every degree of warmth, every drop of water would be built by machines that are never allowed to stop. And a colony does not die in one blast. It fades, quietly, as those machines wear down. Tonight, we ask what would truly make this world our own. If stories like this one, where the real danger hides behind how simple something looks, are the kind of thing you enjoy, it would mean a lot if you tapped like and subscribed. It honestly helps the channel keep making these. Also, before we begin, we're now live on Spotify. The link's in the description if you would like to listen to us wherever you are. Now, with all that being said and done, get yourself comfortable, let's begin. Look up on the right night, and it is there. Not a smudge of light like a distant star, not a rumour glimpsed through a telescope. A whole world, hanging in the dark, close enough that you can trace the shadows of its craters with your naked eye. You have seen it 1,000 times. It has watched over every human being who has ever lived. And because it is always there, always familiar, we have quietly convinced ourselves that we understand it, that it is, in some sense, already ours. A neighbour, a doorstep, the obvious first step into the rest of the universe. That feeling of familiarity is the most dangerous idea we will confront tonight. Because the moon is not a neighbour. It only wears the costume of one. It sits, on average, about 384,000 kilometers away, and yet a beam of light crosses that gap in about 1.25 seconds, near enough that it feels almost within reach. When astronauts traveled there during the Apollo years, the journey took roughly 3 days. 3 days. You could drive across a large country in less time than that and never leave the ground. Compared to Mars, which sits tens of millions of kilometers away even at its closest, the moon is practically next door. And that nearness whispers a promise to us. It says, this one is easy, this one is safe, this is the world where humanity finally learns to live somewhere other than Earth. Hold on to that promise for a moment, because we are going to watch it come apart. Picture the vision the way it is usually sold to you. A cluster of gleaming habitats half buried in grey soil. Solar panels fanned out across a ridge, drinking sunlight. A mining rig chewing patiently into a crater wall. Greenhouses glowing a soft artificial green against the black sky. People in sleek suits walking with that slow, bouncing low-gravity gait, going about their day as casually as commuters. Children, maybe, pressing their faces to a thick window to watch the Earth hang motionless overhead. A city on the moon, a second home for our species. It is a beautiful picture, and versions of it have decorated magazine covers and mission proposals for the better part of a century. But that picture skips something. It skips the single most important distinction in the whole subject. And once you see that distinction, you can never unsee it. Because there is an enormous difference between the words we casually throw around as if they mean the same thing. Visiting the moon. Building a base on the moon. Staying on the moon. Colonizing the moon. Those are not 4 ways of saying one idea. They are 4 completely different achievements, separated by gaps so wide that crossing each one is harder than everything that came before. Think of it as a ladder with 4 rungs. The first rung is visiting. We have already climbed this one, and it remains one of the greatest things our species has ever done. 12 human beings have walked on the surface of the moon. Every one of them arrived during the Apollo program, and every one of them left within days. The longest anyone ever stayed on the surface was during Apollo 17 in December of 1972, and even that record-setting expedition lasted about 3 days before the crew climbed back into their lander and went home. A visit is a spectacular sprint. You bring everything you need on your back, you plant a flag, you gather some rocks, and you leave before the environment has a real chance to grind you down. Visiting proves you can get there and back alive. It proves almost nothing about staying. The second rung is the temporary base. This is where we are pointing ourselves right now. After more than 50 years, humans are returning. In April of 2026, the Artemis II mission carried a crew of 4 on a loop around the far side of the moon and back. The first people to travel that far from Earth in half a century. They did not land. They flew past and returned. The plan that follows has already shifted more than once, which tells you something about how hard even this rung is. Artemis 3, once meant to put boots on the surface, was quietly rewritten in early 2026 into a rehearsal in orbit closer to home. The first actual landing of this new era was pushed to Artemis 4, aimed at somewhere around 2028. And the small station that was supposed to orbit the moon as a waypoint, the one called Gateway, was shelved in March of that same year so that effort could be poured into the surface instead. By May, the agency was naming its first moon-based missions. Take all of that in carefully, and one fact stands out. After a half-century of dreaming, the boldest near-term goal on the table is simply to land a few people and have them survive on the surface for something like a week. Supplied entirely from Earth. That is the second rung, and we have not stood on it yet. A temporary base is a campsite. Everything about it is imported. The air, the water, the food, the power, the shelter, the spare parts, the medicine, the very heat that keeps the crew from freezing. All of it rides up on rockets from the only place in the known universe that hands out these things for free. A campsite can be wonderful. A campsite can do real science. A campsite can stay occupied for months if the supply trucks keep arriving. But a campsite is not a settlement, because the moment the trucks stop, the campsite dies. Its entire existence is a thread stretched back to Earth, and that thread is holding up everything. The third rung is the continuously occupied outpost. This is a base that never empties out. One crew leaves, another arrives, and there is always at least one human on the surface, year after year. We have done something like this in orbit. The International Space Station has kept people living above our heads continuously for more than 2 decades, and it is one of the proudest ongoing achievements of our civilization. But notice what keeps it alive. A steady, relentless stream of resupply ships carrying oxygen, water, food, filters, parts, and experiments. Cut that stream for long enough and the station becomes uninhabitable. A permanent lunar outpost would be the same kind of achievement and the same kind of dependency, just farther away and harder to reach. Continuous occupation is remarkable. It still is not a colony. And that brings us to the fourth rung, the one nobody has ever climbed on any world in the entire history of life on Earth: a colony. A colony is not a bigger base. A colony is a different category of thing altogether. A colony implies permanence that does not depend on outside charity. It implies a population that grows, that includes not just workers on rotation, but families, children, people who are born there and live their whole lives there. It implies the ability to produce the essentials of survival locally, to repair and replace the machinery that keeps everyone alive, to grow food, to make medicine, to manufacture the parts that break, and above all, it implies the ability to survive disruption, to take a hard blow, to lose a supply mission, to watch a critical machine fail, and to keep living anyway, because the settlement can solve its own emergencies without a rescue from home. Here is the distinction stated as plainly as it can be. A base is supplied by Earth. A colony can survive without Earth. And everything that makes the second sentence true is what we are here to understand. Before we leave that ladder, it is worth grounding it in the only places on Earth that come close to climbing it, because they tell us something humbling. We have built isolated human outposts on our own planet, in places nearly as cut off as another world, and even our very best ones are still only bases. They have never once become colonies, and they enjoy every free gift the moon withholds. Consider the research stations deep in the interior of Antarctica, at places like the South Pole and the high frozen plateau. Through the long polar winter, they are physically sealed off from the rest of humanity. For months, the cold and darkness make flights in or out impossible, so a small crew, often only a few dozen people, is left entirely on its own, living on whatever was stockpiled before the last plane departed. They call it wintering over. No resupply, no easy rescue. If something breaks, they fix it themselves or do without until spring. In its isolation, it is one of the closest experiences to living off-world that Earth can offer. And yet, look at what those crews still have for free. Without a single machine. They have air, endless and breathable, the same air the whole planet shares. They have water in almost unlimited supply, because they are standing on a continent of ice that only has to be melted, not mined from frozen shadow. They can step outside. The Antarctic winter is savage and it can kill, but a person can walk out a door and stand under the open sky for minutes, even hours in the right gear, and simply breathe. The environment is hostile, but it is not instantly, absolutely lethal the way vacuum is. Even the most remote station on Earth is wrapped in the planet's free protection. Now take the other great example, and it runs in the opposite direction. A military submarine on a long patrol is a sealed metal tube holding well over 100 people for months at a time, with no resupply and no fresh air from outside. It makes its own oxygen, scrubs its own carbon dioxide, recycles its own water, and manages its own waste, all while cut off from the world. Of everything humans have built, a submarine on patrol is perhaps the closest working model of the life support isolation a lunar habitat would demand. But notice again, the gift hiding just out of sight. A few meters above that submarine is an entire ocean of breathable atmosphere. It can rise, it can surface, it can open a hatch to the sky. The sealed isolation is real, but it is a choice made in the middle of a living, breathing planet that is always there to catch it. Here is the lesson those outposts teach. Both of them are supplied islands. They are self-contained for a season, run by machines and stockpiles, but they are never self-sustaining. Their populations do not grow. No child is born to spend a life at the South Pole or aboard a submarine. They preserve human life for a fixed stretch, and then they are relieved, resupplied, or brought home. They are, in the exact language of our ladder, Bases. Every one of them. And they are bases despite having free air, free water, and an outside a person can survive in. And this is why the deceptive nearness we began with does real damage to how we plan. Because the moon is close, and because we have already been there. The mind quietly files it under solved, a box already ticked, a destination we have merely neglected rather than one we have barely begun to inhabit. For more than half a century, confident forecasts have placed thriving lunar towns just a decade or two away, and each forecast has quietly expired. The pattern is not a failure of ambition or engineering talent. It is that the forecasts were measuring the wrong distance. They measured how far away the moon is, which is small, instead of how far a base is from a colony, which is enormous. The two numbers have almost nothing to do with each other. One is crossed by a rocket in 3 days. The other has never been crossed by anyone, anywhere, and no rocket can cross it for us. There is one more detail worth borrowing from the Antarctic winter, because it previews a problem we will return to. When a station is sealed in for the season and someone falls seriously ill or is badly hurt, there is often no way to get them out. Crews have had to perform emergency medicine on one another, with only the supplies and the training they brought. Sometimes talking to distant doctors by radio, because the outside world simply cannot reach them until the ice releases its grip. That is on Earth, a few hours by air from a hospital in any other season. It is a small, sharp taste of a much larger truth waiting on the moon, where the nearest hospital is a world away and the season never ends. So when someone says we are going to colonize the moon, ask which rung they actually mean. Almost always the images in their head belong to rung 2 or rung 3. The campsite, the occupied outpost, the thread stretched back home. Those are extraordinary and worthy goals, and reaching them will take heroic engineering. But they are not colonization, and pretending they are is how we fool ourselves into thinking the hard part is nearly over when it has barely begun. To understand why that fourth rung is so brutally difficult, you have to stop looking at the beautiful renderings and start looking at the ground those habitats are standing on. Because the reason a lunar colony is so hard has nothing to do with rockets. It has to do with the world itself and what that world does and does not offer to a human body left unprotected on its surface. So let us take an honest inventory of what the moon actually provides for keeping a person alive. Not what it might provide with enough machinery. What it provides naturally, for free, the way Earth provides it to you right now, without you ever having to think about it. Start with air. On Earth, you are standing at the bottom of an ocean of it, 5,000 trillion tons of atmosphere, pressing gently on your skin and filling your lungs with every breath, and you have never once had to earn it. The moon has, for every practical purpose, none. Its surface is wrapped in an atmosphere so thin that scientists call it an exosphere, a whisper of stray atoms so sparse that it barely deserves the name. Step onto the surface without a suit, and there is nothing to breathe, and there is nothing pressing back against the inside of your body. That second part matters as much as the first. Your body is built and pressurized for the weight of Earth's air. Remove that pressure, and the fluids in your tissues begin to turn to vapor. The vacuum does not just fail to feed you, it actively pulls you apart. So on the moon, breathable air is not a resource you find. It is a product you must manufacture, store, circulate, scrub, and replace forever without a single long interruption. Next, water. Liquid water on the surface of the moon does not exist and cannot exist because there is no pressure to hold it and the temperatures forbid it. There is water, and we will spend real time later on the confirmed ice, locked into the coldest, darkest craters near the poles. First proven beyond doubt when a NASA impactor slammed into a shadowed crater in 2009 and kicked up a plume that contained it. But that is not a lake you can dip a cup into. It's ice welded into frozen soil, in places colder than almost anywhere else in the solar system. Between finding it and drinking it lies an entire chain of machines. So drinkable water, like air, is not something the moon gives you. It is something you extract, purify, and guard. Now, temperature. You live inside a narrow, forgiving band of warmth that Earth maintains for you through its atmosphere and oceans and its steady turning. The moon offers no such mercy. With almost no atmosphere to trap or spread heat, its surface lurches between extremes. In direct sunlight, the ground can climb well above 100 degrees Celsius, hot enough to cook. In darkness, it can plunge below minus 150 degrees Celsius, and in the permanently shadowed craters near the poles, it is colder still. Among the coldest natural places we have ever measured anywhere near the sun. And because a single lunar day and night stretches across roughly a month, a spot on the surface can bake in sunlight for about 14 Earth days, and then freeze in darkness for about 14 more. Every stable, survivable temperature inside a habitat would have to be created and defended by machines against a world that swings violently between burning and freezing. Then there is radiation. And this is where the moon's lack of a protective shell becomes truly menacing. Earth wraps you in two invisible guardians. A thick atmosphere and a global magnetic field generated deep in its molten core. Together they deflect and absorb the storm of charged particles that streams constantly from the sun and the far more energetic cosmic rays that arrive from the depths of distant stars. The moon has neither. It has no global magnetic field to speak of, and no atmosphere worth the name. So the full radiation of open space falls onto its surface almost unimpeded. Over days, a visitor can manage the exposure. Over years, for a population meant to live and reproduce there, that constant radiation becomes a slow, grinding threat to human cells and human machinery alike. Shielding is not optional. It is another wall that must be built and maintained. And then, layered on top of all of it, there is the dust. The moon is covered in a fine grey powder called regolith, the shattered remains of billions of years of micrometeoroid impacts with no wind and no water to smooth it. Unlike the rounded sand of an earthly beach, these grains were never weathered soft. They are jagged, glassy and abrasive, and they carry an electric charge that makes them cling to everything they touch. Suits, seals, joints, visors, lungs, machinery. There is real and interesting scientific debate here, and we will get into it honestly later, because recent laboratory work has suggested this dust may be less poisonous to human lungs than the dirtiest city air, even as other studies show its finest particles can damage living cells. But whatever the final verdict on its toxicity, no one disputes that mechanically it is a saboteur, working its way into every moving part and every sealed edge. Even the ground itself is quietly hostile to the machines that would keep people alive. Finally, notice everything that simply is not there at all. No fertile soil teeming with the microbes and nutrients that turn a seed into food. No weather that delivers rain. No breathable sky, no running water, no forgiving margin anywhere. On Earth, if a single system in your life fails, a dozen others quietly catch you. The air is still there, The water still runs. The ground is still warm. The planet itself is a vast, redundant safety net that has been holding life for billions of years. The moon offers no net. Nothing about its natural surface wants you alive, and nothing about it will step in to save you if your equipment falters. It is not malicious. It is simply indifferent, which in a place this extreme amounts to the same thing. Now, put those two halves of the story together, because this is the heart of the whole problem. On one side, you have the ladder, 4 rungs, and a colony sits at the very top, defined by one demanding quality above all others: independence from Earth. On the other side, you have the world itself, a surface that provides on its own essentially none of the conditions a human body needs. Not air, not pressure, not water you can drink, not stable warmth, not protection from radiation, not soil that grows food, not a shred of forgiveness. Stack those two facts against each other, and the true shape of the problem finally appears. To climb to that 4th rung, a lunar colony would have to manufacture and maintain on its own nearly every single condition that Earth hands to you for free right now. Every breath of air would be built by a machine. Every degree of warmth held against the vacuum by a machine. Every drop of water pulled from frozen soil by a machine. Every barrier against radiation, every safe place to sleep, every pressurized room where a person can take off a helmet and simply exist. All of it manufactured, all of it maintained, all of it kept running without a long pause on a world that will punish the smallest failure. This is the thesis that everything ahead will unfold. So let us state it clearly, and then let it grow. The horrifying problem with colonizing the moon is not that we cannot reach it. We have reached it. It is not that we cannot land on it, or build on it, or survive there for a while. We can do all of that, and soon we will. The horrifying problem is that a true colony would have to recreate enough of Earth's biological and industrial support systems to survive indefinitely on a world that offers no natural margin for failure, while remaining at first almost completely dependent on Earth-built machines, Earth-trained experts, and Earth-shipped parts to do it. Every system a settlement adds to protect its people from the moon becomes one more system that can break. And on the moon, when the thing keeping you alive breaks, there is no open window to throw open, no stream to walk to, no warm night air waiting outside. There is only the next machine, and the machine after that, all the way down. That is why the deceptive closeness of the moon is such a trap. Its nearness is real, and it is a genuine advantage. If something goes wrong, help from Earth is days away rather than the many months a Mars crew would have to endure. And later that difference will matter enormously. But nearness solves the problem of getting there. It does nothing to change the surface once you arrive. A settlement 3 days from home is still surrounded by vacuum, still baked and frozen by turns, still bathed in radiation, still utterly dependent on the machines humming around its people. Proximity shortens the rescue. It does not remove the danger. And a colony that can always be rescued is, by definition, not yet independent. It is not yet a colony at all, which leaves us standing at the edge of the real subject. We have seen the ladder and we have seen the world. We have seen that a colony means independence, and that the moon grants none of the conditions independence would require. So the natural next question is the one that will carry us into what comes next. If nothing survivable exists on the surface, then survival has to be built. It has to be enclosed, sealed, pressurized, and kept alive by an unbroken chain of equipment. That enclosure is not a house. It is a machine, a permanent survival machine wrapped around fragile human bodies, and it can never, not for one careless hour, be allowed to fully stop. So before we can talk about mining the moon, or growing food on it, or raising children under its black sky, we have to step inside that machine and understand exactly what it takes to keep a single human being breathing behind a thin wall, with a vacuum on the other side that is patiently, silently waiting to get in. That is where we go next. We left off at a threshold, standing at the edge of a thin wall with a vacuum waiting on the other side. Now we step through it, into the pressurized space where the people actually live. And the first thing you have to unlearn is the word house. A house on Earth is a convenience. It keeps the rain off and the cold out, but if the roof leaks or the furnace dies, you are inconvenienced, not killed. The air keeps flowing in through every crack. The house is optional in the deeper sense, because the planet outside it is already keeping you alive. A lunar habitat is the opposite. It is not a shelter sitting inside a livable world. It is the only livable world, a fragile bubble of Earth-like conditions held together by machinery, surrounded on every side by a place that would end you in under a minute if the bubble failed. It is less a building than an aquarium running in reverse. In an aquarium, the water and the life are on the inside of the glass, and the dry, breathable room is safe all around it. Here it is flipped. The breathable life is on the inside, and the deadly, airless void is the room. And the glass, in this case, is the only thing standing between the two. So the question that governs everything is brutally simple. What does it take to keep that inside alive? And the answer is a chain of machines so long, so interlocked, and so unforgiving that once you understand it, the phrase permanent settlement starts to sound less like a promise and more like a dare. Begin with the air, because the air is where the illusion of permanence dies fastest. You do not simply fill a habitat with oxygen and seal the door. Air on a spacecraft or a sealed base is not a supply you top up. It is a loop you run, continuously, for as long as anyone is breathing, and a human being is a surprisingly demanding passenger in that loop. Every day, an adult consumes something in the neighborhood of 800 grams of oxygen and exhales roughly a kilogram of carbon dioxide, along with water vapor and heat and a slow drizzle of other trace gases. Multiply that by a crew, multiply it by every hour of every day, with no pause, forever. The loop has to add oxygen at exactly the rate people burn it, and it has to remove carbon dioxide at exactly the rate people breathe it out. And it has to do both without ever falling behind, because falling behind is fatal in a way that is quiet and fast. Here is the part that people rarely appreciate. On the moon, running out of oxygen is not even the most immediate danger. Long before the oxygen runs low, the carbon dioxide you exhale will get you. In a sealed volume, exhaled carbon dioxide accumulates, and it becomes dangerous at concentrations that are still a rounding error compared to the oxygen still present. Rising carbon dioxide brings headaches, then confusion, then a creeping impairment of judgment precisely when clear judgment is most needed, then unconsciousness. The gas that kills you is not the one you are missing, it is the one you are making, which means the single most important machine in the entire habitat is not the oxygen generator. It is the scrubber, the device whose only job is to pull carbon dioxide back out of the air faster than the crew can produce it. We have watched how thin that margin is. During the Apollo 13 emergency in 1970, the crew's real crisis after the explosion was not a dramatic loss of air. It was carbon dioxide climbing inside their crippled craft toward levels that would have quietly killed them, forcing an improvised fix cobbled together from spare parts and instructions rid up from the ground. That was 3 people for a few days, with Earth on the radio the entire time. Now imagine that same category of failure at a permanent base, with a scrubber that has been running without rest for years, its chemical beds aging, its fans wearing, its seals slowly clogging with the ever-present dust. The scrubber cannot take a day off. It cannot wait for the next supply ship. It is holding back an invisible tide that the crew themselves generate simply by being alive. And the moment it falls behind, the countdown starts. And carbon dioxide is only the loudest of the poisons the crew must keep out of their own air. A sealed habitat slowly fills with a quieter chemical haze that has nowhere to go. The human body itself gives off a steady trickle of trace gases, ammonia, methane, and dozens of others, in sweat and breath and skin. The materials the base is built from add their own. Plastics, adhesives, insulation, electronics, and paints all release faint wisps of vapor as they age and warm, a process called off-gassing. And among those wisps are genuinely dangerous compounds like carbon monoxide and formaldehyde. On Earth, you never notice any of this, because the open atmosphere endlessly dilutes and carries it away. In a sealed volume, there is no away. Every molecule the crew and the machines exhale stays inside unless something removes it. So the life support system needs yet another layer, a set of filters and catalytic units whose entire job is to hunt down these trace contaminants and destroy them before they accumulate to harmful levels. It is a second, subtler scrubber running alongside the first, watching for poisons measured in the faintest traces, and it too must never fall behind. The habitat is, in a quiet and permanent way, always at risk of poisoning itself with its own exhalations, and only a machine stands between the crew and that slow tide. Then there is the oxygen half of the loop, and here the chain of dependency stretches out and reveals itself. Where does the fresh oxygen come from? The most practical answer is to split water. Run an electric current through water and it separates into hydrogen and oxygen. The oxygen goes into the air the crew breathes. It is elegant, and it works, and it is exactly how oxygen is generated aboard the International Space Station right now. But look at what that one sentence quietly requires. It requires water, which on the moon must be extracted from frozen soil by another set of machines we have not even reached yet. It requires electricity, a great deal of it, which must be generated and stored by yet another system. And it requires the electrolysis unit itself to keep functioning, with its membranes and electrodes and plumbing intact. Pull any one of those 3 threads and the oxygen stops. The air machine depends on the water machine, which depends on the power machine, which depends on machines of its own. Nothing on the moon stands alone. Every system leans on 2 or 3 others, and each of those leans on more. And air is only the first of the loops. There is water. A human needs to drink, but a human also sweats, exhales moisture, and produces waste. And in a place where every liter had to be dragged up out of a frozen crater or hauled from Earth at ruinous cost, you cannot afford to throw a single drop away. So the water too becomes a loop. It gets recycled over and over from wastewater and humidity, and yes, from urine, cleaned and filtered, and returned to the tap. Aboard the International Space Station, the water recovery systems already reclaim the overwhelming majority of the water the crew uses. A genuine triumph of engineering, And even there is a constant maintenance headache of filters and distillation units and biological growth that has to be fought back continuously. On a self-sufficient colony, the recycling would have to be even tighter, even more relentless. And every stage of it is one more machine that cannot be allowed to fail for long. Now, hold the air loop and the water loop in your mind at once, and add a third demand that never sleeps: temperature. We touched earlier on the moon's savage swings, the searing sunlit heat, and the deep, frozen dark, and we will return shortly to the long night that drives them. Inside the habitat, none of that is allowed to reach the crew, whatever the world outside is doing. The temperature has to stay in the narrow, comfortable band that human bodies and human electronics both require, and it has to stay there while the world outside lurches between extremes. And this is where the vacuum plays a cruel trick. On Earth, when a machine or body makes too much heat, the surrounding air carries it away. Heat flows into the air, the warm air rises and moves off, cooler air takes its place. That process, convection, is happening around you constantly, and you never think about it. In a vacuum, it does not exist. There is no air to carry heat away. A habitat sitting in sunlight cannot simply let the breeze cool it, because there is no breeze, and there never will be. The only way to shed heat into the void is to radiate it away as infrared, using large panels called radiators, and radiating heat is a slow, difficult, area-hungry business. So the same base that must be heated through the 2-week night must also be actively cooled through the 2-week day, and both jobs fall entirely on machinery. Thermal control on the moon is not a thermostat. It is a permanent, powered war against a world that is always either stealing the crew's heat or dumping too much of it on them. Step back and look at what we have assembled so far. Air that must be generated and scrubbed without pause, water that must be recycled without loss, heat that must be added and removed without rest. 3 loops, running every second, each one dependent on power and on the others, each one a machine or a chain of machines, none of which can ever fully stop. And we have not yet stepped outside. We have not yet dealt with the wall itself, the thin glass of our reversed aquarium, holding all of this precious, manufactured, Earth-like life, apart from the nothing that surrounds it. That wall has to do something almost paradoxical. It has to hold pressure in. Remember that the human body is built for the weight of Earth's air pressing on it from all sides. A habitat has to recreate roughly that pressure inside, which means the walls are not holding the vacuum out so much as holding a great pressure in, straining outward against the emptiness like the skin of an inflated balloon. Every square area of that wall is being pushed on from the inside by the air the crew depends on, and pushed on hard. A breach does not gently equalize, it vents. Air rushes toward the hole, and with it goes the warmth and the pressure and the survivable world the crew has spent enormous effort to build. A large enough breach empties the room faster than anyone can react. And the smaller breaches, the slow ones, are in their own way more insidious because they do not announce themselves. Every sealed pressure vessel leaks. A little. Even the finest ones. Gas finds its way out through seams, through seals, through the microscopic imperfections in any joint, through the airlocks that must open and close every single time a crew member goes outside and comes back. On the International Space Station, keeping the air from slowly bleeding away is an ongoing task, and there have been real incidents of small leaks that had to be hunted down and patched. Now make the wall permanent. Make it endure years of thermal expansion and contraction as the base heats and cools year after year, each cycle flexing the structure a little. Make it endure the constant peppering of the environment we are about to describe. And coat every seal and every seam and every moving airlock gasket in that fine, jagged, clinging dust that works itself into every gap. A seal fouled by dust does not fail all at once. It fails a little, and then a little more, and the leak rate creeps upward, and the machine that makes oxygen has to work slightly harder to replace what is quietly escaping, and the whole loop tightens by another notch. Maintenance is not an occasional event on the moon. It is the permanent condition of staying alive. There is one more danger sealed inside that wall with the crew, and it is the one every submariner and every astronaut fears most, because in an enclosed world it has nowhere to be contained. Fire. On Earth, a fire is terrible, but it is local. You can flee it, seal a door on it, or step outside and breathe clean air while it burns itself out. Inside a habitat, there's no outside to flee to. A fire in a sealed jar does not just threaten to burn people, it threatens to consume the very oxygen they are breathing, and to flood the whole shared volume with smoke and toxic fumes that the crew cannot escape, because the only air anywhere is the air the fire is poisoning. And the danger is sharpened by the way life support works, because keeping the atmosphere rich enough in oxygen for people to breathe comfortably is exactly the condition that lets flames spread fast and hot. Every material inside must be chosen for how reluctantly it burns. Every electrical fault in a place packed with power systems and wiring is a possible ignition. Detection has to be near instant, and suppression has to work without simply venting the crew's air to space. A fire that would be a manageable emergency in a house on Earth is, in a lunar habitat, a contender for the fastest way an entire settlement could die, and defending against it is one more system that must stand ready every second and never once be wrong. So let us finally step outside, because outside is where the environment stops being a passive backdrop and starts actively attacking the machines that keep the crew alive. And then there is the single most abused doorway in the entire settlement. The one weak point that must be deliberately opened to the enemy over and over again. The airlock. Every time a crew member goes outside to work, and every time they come back, they must pass through this chamber, which fills with air to let them in from the vacuum, and then empties that air to let them out into it. It is the one place where the deadly outside is invited, by design, right up against the living inside, held back only by a set of doors and seals that must cycle flawlessly every single time. Each cycle is a small gamble. Each cycle flexes the seals, works the mechanisms, and, worst of all, drags in that clinging, abrasive dust on suits and boots, packing it into the very gaskets that must hold the vacuum out. An airlock is a revolving door between a survivable world and an instantly lethal one, and it may cycle several times a day for years. It cannot jam with a crew member half inside. It cannot fail to seal. It cannot let its dust-fouled gaskets degrade past the point of holding pressure. Of all the machines that cannot stop, the airlock is the one that must repeatedly, deliberately touch death and close again. The first assailant is radiation, and its danger is not only to bodies, but to hardware. We spoke earlier of the moon's lack of a magnetic shield and atmosphere, and how that leaves the full storm of space radiation falling onto the surface. There are two flavors of it, and both matter here. There is the steady, ceaseless drizzle of galactic cosmic rays, high-energy particles arriving from across the galaxy, sleeting through the surface every hour of every day. And there are the sudden, violent outbursts from the sun, solar particle events, when our star hurls out a burst of charged particles that can spike the radiation on the surface dramatically over the course of hours. For a crew, the steady drizzle is a long-term health threat, and the solar outbursts are an acute, potentially lethal one that they must be able to hide from behind heavy shielding on short notice. But for the equipment, radiation is a slow corrosion of a different kind. Electronics are vulnerable to it. Radiation can flip the bits in a computer's memory, degrade the delicate materials and circuits, and gradually wear down the very systems the colony most needs to keep running. So the machines must not only run continuously, they must run continuously while being slowly damaged by the environment they are running in. The second assailant comes without warning and without mercy. Micrometeoroids. Space is full of tiny particles of rock and metal, most of them minuscule, traveling at speeds so enormous that even a fleck can strike with the energy of a bullet. On Earth, the atmosphere burns these up into shooting stars long before they reach the ground. Another quiet gift you never think about. The moon has no such defense. These particles hit the surface directly, and they hit anything on it directly too. Habitats, radiators, solar panels, spacesuits, antennas, exposed machinery. Most strikes are too small to matter individually, but they accumulate. They pit and scar and puncture. Over years, the outer surfaces of everything exposed are slowly sandblasted by a rain of hypersonic grit. And any single unlucky strike on the wrong component, a radiator line, a suit joint, a pressure seam, is a problem that must be found and fixed before it grows. And the third assailant is the one we have been circling this entire time. The dust. We have mentioned it in passing, but here is where it earns its place as perhaps the most relentless enemy of the machines. This is the regolith, the fine grey powder of shattered rock we described earlier, and its danger is mechanical and constant. It clings to everything by electrostatic charge, so that every time a crew member goes outside and comes back, they track it into the airlock, and from there it drifts through the habitat, working into keyboards and hinges and human lungs. It is abrasive in a way that ordinary dust is not, because its grains were never weathered smooth. So it does not just settle on machines, it grinds them. It infiltrates bearings and gears and seals, and slowly wears them down from the inside. During the Apollo missions, which lasted mere days, the crews were already astonished at how thoroughly the dust invaded everything, jamming zippers, coating visors, abrading suit fabric, clinging so stubbornly that it could not be brushed off. Those were visits of a few days. Now stretch that assault across years, across a settlement full of moving parts and delicate mechanisms, all of them trying to run continuously in a fog of the most invasive material imaginable. Every mechanism the colony depends on is being quietly sabotaged by the very ground it stands on. Radiation degrading the electronics, micrometeoroids scarring the surfaces, dust grinding down the moving parts, and all of it happening to machines that, remember, are not allowed to stop, because stopping means the air loop or the water loop or the heat loop falters, and behind that thin wall, a crew is depending on all of them at once. Now add the cruelest scheduling problem of all, the one that ties every previous point into a knot: power. Every machine we have described, the scrubbers, the oxygen generators, the water recyclers, the heaters, the coolers, the pumps and fans and lights, all of it runs on electricity, and lots of it. The obvious source is the sun, and sunlight on the moon is abundant and constant when it is available. But there is that word again, when it's available. Because across most of the moon, that roughly 2-week day is followed by a roughly 2-week night. And during that night, for about 14 Earth days at a stretch, the solar panels produce nothing at all. 14 days of darkness. 14 days in which every life-critical machine still has to run, still has to hold back the carbon dioxide and generate the oxygen, and, above all, keep the crew from freezing in a cold that plunges below minus 150 degrees Celsius. Batteries alone cannot carry a settlement through 2 weeks of continuous full power demand. The mass of batteries required would be staggering. So the long lunar night forces the colony toward other answers, most seriously toward compact nuclear power, small fission reactors designed to generate electricity steadily, regardless of whether the sun is up. It is a genuine and promising path, and it is being actively developed, but knows that it is one more complex, Earth-built machine with its own maintenance needs, its own finite parts, and its own catastrophic failure modes, added to a settlement that already cannot afford to lose a single critical system. It is worth pausing on why the settlement is pushed so hard toward nuclear power in the first place, because the reason reveals how tight the bind really is. The obvious alternative is to store up energy during the 2-week day and live off it through the 2-week night, the way a home battery stores sunlight for the evening. But run the numbers and the scale becomes crippling. To carry a base and all its life-critical machines through roughly 14 straight Earth days of darkness on stored charge alone would demand a mass of batteries so enormous that hauling it to the moon becomes its own impossibility. Batteries are heavy, and 2 weeks is a very long time to keep every heater and scrubber and pump running from a charge with nothing coming in. That is why serious plans turn to fission. A compact reactor makes its own steady power around the clock. Day or night, sunlight or shadow, indifferent to the lunar sky, which is precisely what a settlement in the long night needs. But a reactor is not a quiet gift. It carries its own heavy shielding to protect the crew from its radiation. It needs to shed its own waste heat into the same unforgiving vacuum that already makes cooling so hard. Its fuel is finite and, for now, entirely an import from Earth. And it concentrates a great deal of the colony's survival into a single, complex machine, so that its failure would not be an inconvenience, but a countdown. The solution to the long night is real. It is also one more irreplaceable heart that the settlement cannot afford to let stop. This is why so many serious concepts for a lunar base cluster near the poles, in that select geography we will come to shortly, where a few high ridges catch sunlight for far longer stretches, and the darkness is not quite so absolute. The moon's map is not uniform, and where you plant a settlement changes which of these problems bites hardest. But no location erases the fundamental bind. The bind is this, and it is worth stating as the central discovery so far. Every single system a settlement builds to protect its people from the moon becomes, in the same instant, one more system that can fail and must be maintained. The wall that holds the pressure in can leak. The scrubber that removes the carbon dioxide can clog. The generator that makes the oxygen can break. The recycler that saves the water can foul. The radiators that shed the heat can be punctured. The reactor or the panels that power all of it can falter through the long night. And each of those machines is being actively worn down by radiation, by micrometeoroids, and by the ever-present grinding dust, while being forbidden ever to stop. This is the dependency trap in its purest mechanical form. The more thoroughly a colony protects itself from a hostile world, the more machinery it must keep perfectly, endlessly alive, and the more places there are for a fatal failure to begin. And here the trap tightens further, because of a conflict that engineers know intimately and cannot escape. The obvious defense against a machine failing is redundancy, carrying a backup and a backup for the backup. If the scrubber fails, you want a second scrubber ready. If a reactor falters, you want a second source of power. But every backup is mass, and mass is the one thing that is savagely, unforgivingly expensive to lift off the Earth and land softly on the moon. Every kilogram of spare hardware you send is a kilogram you did not spend on food, or water, or people, or the next expansion. So a settlement is caught between two merciless pressures. Carry too little redundancy, and a single failure can cascade into catastrophe. Carry enough redundancy to be truly safe, and the launch mass becomes impossible. There is no comfortable middle. There is only a running, permanent gamble about which systems get a backup, and which ones the colony simply has to pray never break at the wrong moment. Which raises the obvious escape, the one that seems to solve everything, and the one we will turn to next. If lifting mass from Earth is the bottleneck, and if the moon itself is made of rock and ice and metal, then surely the answer is to stop importing and start producing. Stop shipping oxygen and pull it out of the moon's own soil. Stop hauling water and mine it from the frozen craters. Stop landing every beam and panel and instead build from the ground beneath your feet. This is the great hope of every serious plan for a permanent settlement. The promise that the moon can begin to supply itself, loosening the thread back to Earth, one strand at a time. It is a real hope, and some of it is genuinely achievable. But it comes with a hidden catch. A line between the problems local resources can solve and the ones they cannot touch. And that line turns out to be the difference between a base that leans a little less on Earth and a colony that could truly survive without it. So before we mine a single crater, we have to ask the harder question. When the moon starts feeding itself, what exactly does that solve? And what does it leave completely untouched? That is where we go next. We ended the last stretch on an escape hatch. If the crushing problem is that everything must be lifted from Earth at ruinous cost, then the answer seems almost obvious. Stop lifting. The moon is not empty. It is a whole world of rock and metal, and, in its coldest hidden corners, frozen water. So instead of shipping every breath and every drop and every beam up the gravity well, why not make them on the spot? From the ground beneath the settlement's feet? Loosen the dependence on Earth one strand at a time until the base begins, at last, to feed itself. This is the great hope of every serious plan for a permanent lunar presence. Engineers call the idea living off the land, or making use of local resources, and it is not a fantasy. Parts of it are real, achievable, and already being tested on the surface. So let us be scrupulously fair to it. Let us give the moon full credit for everything it genuinely could provide. And then let us find the exact line where that credit runs out, because that line is where a base and a colony finally, permanently part ways. Begin with the resource that captures every imagination. Water. We noted earlier that a NASA impactor, the L-Cross mission, deliberately slammed into a permanently shadowed crater near the moon's south pole in 2009, and that the plume it kicked up contained water. That result was a milestone. Before it, water on the moon was a strong suspicion. After it, it was a confirmed fact. There is water ice on the moon, concentrated in the floors of certain craters near the poles, places where the sun never rises above the rim and the temperature stays permanently, astonishingly cold. And water, if you could get it, is the single most valuable substance a lunar settlement could hope to find. Because water is not just water. Split a molecule of water and you get hydrogen and oxygen. The oxygen can go straight into the air the crew breathes, feeding the very loop we traced earlier, and it can also serve as the oxidizer that lets rocket engines burn. The hydrogen paired with that oxygen is rocket propellant, the fuel that could let vehicles launch back off the surface without hauling every gram of it up from Earth. And the water itself, of course, is drinking water. The thing a human body cannot survive 3 days without. Air, fuel, and drink, all latent in a single frozen resource. It is easy to see why the polar ice is talked about the way earlier generations talked about gold. But now the reality check, and it is a firm one. The word ice invites you to picture something it is not. There are no frozen lakes on the moon. There are no glittering slabs waiting for astronauts to cut them into blocks like ice from a winter pond. Everything we have learned suggests the water is mixed into the soil, present as scattered grains and thin coatings and patchy deposits, welded into the regolith across the floors of these shadowed craters, and possibly buried beneath a layer of dry material on top. Its exact concentration, its depth, its distribution, how much of it sits where a machine could actually reach it, all of that still matters enormously and is still being mapped. You do not arrive at the pole and turn on a tap. You arrive and face the problem of pulling sparse ice out of frozen dirt in the most hostile mining environment ever contemplated. Consider where this ice lives. It lives in permanent shadow, in craters the sunlight has not touched for perhaps billions of years, at temperatures that can sit below minus 200 degrees Celsius, cold enough that the ice has stayed frozen in place for perhaps billions of years. A mining machine sent into one of those craters must operate in total darkness, so it carries its own light and its own power into a place the sun never warms. It must function where ordinary lubricants would freeze solid, where metals grow brittle, where the cryogenic soil behaves in ways no terrestrial mine has ever dealt with. It must move across rugged, unmapped crater floors that swallow radio signals and confuse navigation. And then, having somehow dug up icy regolith in that frozen dark, it must heat it to drive the water off as vapor, capture that vapor before it escapes back into vacuum, and purify it, all without the water refreezing or bleeding away at every step. Early robotic missions have begun the very first probing of this problem. A drilling and analysis experiment called Prime 1 rode to the surface in 2025 to test the basic act of digging into polar soil and sniffing for volatiles. And other nations are racing to the same ground with a Chinese mission, Chang'e 7, aiming for the Shackleton crater region and carrying a hopping probe designed to peer into permanent shadow. These are first steps, tentative and enormously difficult, toward a resource that is genuinely there and genuinely hard to hold. So credit where it is due. The water is real. The chemistry is real. If the extraction machines can be made to work reliably, the ice could supply drinking water, breathing oxygen, and rocket propellant. And that would loosen the thread back to Earth in a real and important way. But notice that every gain here is a gain in consumables, the things a body uses up. Water, air, fuel, precious, yes, but these are the easy end of self-sufficiency. And even they demand a chain of temperamental machines running in the worst conditions imaginable. Now widen the view beyond the poles, because there is a second local resource that covers the entire moon, and it is the ground itself. The regolith, the fine grey soil we have already met as an enemy, is also, remarkably, a treasure. By mass, lunar regolith is very roughly 40 to 45% oxygen, locked chemically into the minerals and metal oxides that make it up. That oxygen is not free to breathe, it is bound up in rock, but it can be pried loose. Heat the regolith and run electricity through it in the right way, or react it with hydrogen at high temperature, and you can strip the oxygen out of the minerals, capturing it as breathable gas while leaving behind metals as a byproduct. This is not exotic in principle, and prototype systems to do exactly this have been built and tested on Earth in preparation. It means that even far from any polar crater, a settlement standing on ordinary lunar dirt is standing on an oxygen mine, if it has the power and the machinery to work it. But the phrase, "if it has the power," hides the whole difficulty, and it is worth opening up, because prying oxygen out of solid rock is one of the most energy-hungry things a colony could attempt. There is more than one way to do it, and each is its own industrial process. One approach, called hydrogen reduction, heats the regolith and passes hydrogen over it, coaxing the oxygen in certain iron-bearing minerals to combine into water, which is then split to release its oxygen. Another molten regolith electrolysis is more brutal still. It heats the soil past the point of melting to well over 1,000 degrees Celsius, until it becomes a glowing liquid, and then drives a powerful electric current through the melt to tear the oxygen free directly, leaving molten metal behind. A third, carbothermal reduction, uses carbon and intense heat to work the same kind of chemistry on the rock. Every one of these methods has been demonstrated in laboratories on Earth, so none is science fiction. But know what they all have in common: heat, and a great deal of it. Melting rock and holding it molten, or baking soil at furnace temperatures for hours, consumes staggering amounts of energy, and it consumes that energy continuously for a stream of oxygen that a crew burns without pause. So, the oxygen mine does not stand apart from the power problem we wrestled with earlier. It sits directly on top of it. To breathe the moon's own oxygen, a settlement must first win an enormous and unbroken supply of power, and then feed most of it into furnaces that turn dirt into air. The resource is real. It is simply that the moon charges for it in electricity, and the bill never stops arriving. And the leftover from that process points to a third gift. When you tear the oxygen out of regolith, you are left with metals, iron, aluminum, titanium, silicon, the raw structural elements of any industrial society, sitting in the tailings. On top of that, the regolith itself, unprocessed, is a construction material. It can be piled thick over a habitat to form a shield, and here it earns back some of the fear it caused earlier, because a few meters of regolith heaped over a shelter block's radiation stops micrometeoroids and buffers the wild temperature swings all at once, using nothing but the free dirt that surrounds the base. Regolith can also be sintered, heated until its grains fuse into solid bricks and slabs, and even three-dimensional printed structures, so that a settlement might one day print its own landing pads and walls and radiation berms from local material instead of importing every panel. The most elegant version of this idea skips the piling and the printing altogether and goes underground. The moon has natural caverns, lava tubes, hollow tunnels left behind by ancient flows, some of them apparently large enough to shelter substantial structures. A habitat placed inside of one of these, or simply buried beneath the surface, would be shielded from radiation and micrometeoroids, and the 2-week temperature swing by the mass of the moon itself, solving several of the deadliest problems we have met in a single move. The surface is where the moon is most hostile. A few meters down, it is merely cold and dark and still. Add one more local resource, and it is the one we were just worrying about. Power. Across most of the moon, the 2-week night starves the solar panels. But the map is not uniform, and near the poles there are certain high ridges and crater rims that catch sunlight for far longer stretches than the lowlands, some of them illuminated for the great majority of the lunar year. These peaks of near-perpetual light are prime real estate, precisely because a solar array planted there escapes much of the crippling darkness that dooms panels elsewhere. Site a settlement carefully, on a sunlit polar ridge within reach of a shadowed crater full of ice, and two of the hardest problems, power and water, ease at the same time. This is exactly why the South Polar region, and not the equatorial plains the Apollo crews visited, dominates the modern planning, and why the coming landings are aimed there. So let us total up honestly what the moon can give. It can give water, and from water, oxygen and propellant and drink. It can give oxygen again from its very soil. It can give metals as a byproduct, and shielding and building material from raw regolith, and natural shelter underground. It can give near continuous power on a few select ridges. Every one of these is real, and together they would let a settlement replace some of the mass it now must import, and stockpile the propellant that makes coming and going cheaper. In May of 2026, when the agency named its first surface-based missions, this is the frontier it was pointing at. The very beginning of a settlement that leans a little less on home. That is genuine progress, and it deserves to be called that. It is worth heading off a hope that often appears at exactly this point. The idea that the moon will simply pay for its own colonization by becoming a mine that ships treasure back to Earth. The most famous version of this dream is helium-3, a rare form of helium that is genuinely more common in lunar soil than on Earth, and that is often described as a perfect fuel for future fusion reactors. Set aside for a moment that fusion power itself remains unproven as a practical energy source, so the market for this fuel does not yet exist. Look instead at what mining it would take. Helium-3 is spread through the regolith in concentrations so thin that harvesting a usable amount would mean processing staggering quantities of soil across vast stretches of the surface. A strip mining operation of almost absurd scale for a very slight return. But here is the deeper point, and it holds for every dream of lunar riches, whether helium-3, or rare metals, or anything else. Even if such mining could be made to pay, profit is not the same thing as self-sufficiency. A mine that ships its product back to Earth for money is not a world becoming independent. It's a world being harvested, its value flowing outward to the home planet, its supply lines to Earth thickening rather than thinning. Economics might one day give someone a reason to fund a lunar settlement. It would do nothing by itself to make that settlement able to survive without the planet it is selling to. The same holds for the gentler lunar economies people imagine, tourism for the wealthy, or selling propellant to passing spacecraft from a lunar fuel depot. Each could, in principle, bring money and traffic to the moon, and each would be a real achievement. But money and traffic are still not the same as a settlement that can feed, heal, and repair itself when the traffic stops. An economy gives a colony reasons to exist and resources to grow. It does not, on its own, give the colony the ability to survive being cut off, which is the one test that separates a base from a world. Wealth and independence are different currencies, and only one of them keeps a colony alive when the ships stop coming. And now, we arrive at the line. Because the moment you have listed everything local resources can provide, you are forced to confront the far longer list of everything they cannot. And that second list is where the dream of self-sufficiency runs into a wall it cannot climb by mining. Here is the sharpest way to see the divide. Everything the moon can readily supply is a raw consumable or a raw material. Water, oxygen, bulk metal, dirt for shielding. These are the outputs of a well. What a colony actually needs to survive without Earth is not a well. It is a hospital, a factory, a laboratory, and a pharmacy, all at once, and none of those come out of the ground. A well gives you water. It does not give you the dialysis machine, the antibiotic, the circuit board, or the technician who knows how to fix all three. And the gap between the well and the hospital is the gap between a base and a colony. Start with the most damning example: electronics. Every machine we have described across this entire story, the scrubbers, the oxygen generators, the water recyclers, the reactors, the mining robots, the communication systems, the medical instruments, every one of them runs on computer chips and sophisticated electronics. And a modern microchip is arguably the single hardest object our civilization knows how to make. Producing one requires ultra-pure silicon refined to a standard almost beyond imagining. Clean rooms cleaner than any operating theatre. Machines that etch features finer than a wavelength of visible light. Dozens of rare and carefully processed elements gathered from mines, scattered across the entire Earth. And an unbroken chain of specialized suppliers and human expertise that took our whole planet decades to assemble. You cannot mine a microchip from a crater. You cannot sinter one from regolith. A lunar settlement for generations would have no conceivable way to manufacture the electronic brains that every one of its life support machines depends on. And when those chips fail, as chips do, degraded by exactly the radiation we described earlier, the replacements would have to come from precisely one place: Earth. Now widen it. Medicines. A colony of any real size will get sick, get injured, develop the ordinary and extraordinary ailments of human bodies, and it will need pharmaceuticals to treat them. Modern medicines are products of intricate chemistry, synthesized through many careful stages from precursor compounds, purified, tested, and quality controlled, many of them requiring refrigeration and a shelf life that runs out. You do not extract an antibiotic from lunar soil. Manufacturing even a modest range of essential drugs requires a chemical industry, feedstocks, control conditions, and expertise that a small frontier settlement simply would not possess. The colony's medicine cabinet, like its computer chips, would be an import, and a perishable one, tethering the settlement's health directly to the supply line. Now the materials themselves, beyond bulk metal. The moon can give you iron and aluminum and titanium in crude form. It cannot easily give you the specific high-performance alloys engineered for particular jobs, the specialized polymers and plastics, The lubricants formulated to work across brutal temperature ranges, the flexible airtight fabrics of a spacesuit, the membranes inside the water recycler, the seals that hold the pressure in. These are the products of a deep materials industry, refined and blended and formed with precision. Raw regolith metal is the very first step of a 1,000-step journey, and the settlement would be missing nearly all of the remaining steps. And here we reach the deepest problem of all, the one that swallows every other. Even setting aside chips and drugs and exotic materials, suppose the colony wanted to manufacture something simpler, an ordinary replacement part for one of its own machines. To do that, it does not merely need the raw metal, it needs the machines that shape the metal. The furnaces, the mills, the cutters, the precision tools, the calibration instruments, the testing equipment, and those machines are themselves complex products that wear out. And when they wear out, they need replacement parts of their own, which need other machines to make them, which need still other machines behind those. This is the pyramid of tools that make tools, and on Earth it is invisible only because it is so vast and so complete that we never see the bottom of it. Every simple object in your life sits atop a towering, planet-spanning pyramid of mines, refineries, factories, and specialists, each layer making the tools the layer above depends on. A colony cannot ship the pyramid. It can ship the top few layers, the finished machines, and it can perhaps, someday, build a thin slice of the layer beneath. But to be truly self-sufficient, it would have to reconstruct enough of the entire pyramid that it could make the machines that make the parts that keep the machines that keep it alive running. No settlement in the foreseeable future comes remotely close to that. And this is the exact reason a lunar base could look thriving and remain, at its foundation, an extension of Earth's industry rather than a replacement for it. There is a cruel recursion hiding in this that deserves to be named directly. To repair the settlement, you need spare parts. To make spare parts locally, you need manufacturing machines. Those manufacturing machines are more complex than many of the parts they produce, so they themselves need spare parts and specialized repair, which need yet more machines. The problem of self-sufficiency does not shrink as you solve it, it refracts. Each machine you add to reduce dependence on Earth is itself a new dependence, a new thing that can break and that you may not be able to fix on your own. And so, repairing and replacing the settlement's machinery can turn out to be harder than building the settlement was in the first place. Because building it, you had all of Earth's industry behind you, and repairing it, you have only what you managed to carry and what you managed to reconstruct. Even the gentle green promise of growing food runs into this same wall. Yes, a colony would need agriculture, and growing plants in controlled chambers is something we broadly know how to do. But doing it as a genuine, reliable food supply for a population, in closed chambers, with artificial light drawing enormous power, in engineered growing medium since lunar regolith is not living soil, with the water and nutrients and atmosphere all managed by, once again, machines, is an industrial undertaking of its own, and it depends on the same electronics, the same pumps, the same power, the same spare parts as everything else. Agriculture does not escape the pyramid. It sits on top of it like all the rest, and agriculture drags with it a problem that a base can ignore and a colony cannot. Waste. On a short mission, human waste is simply a thing to store, stabilize, and eventually send away or leave behind. Because everything the crew eats was shipped up ready to go. But a settlement trying to grow its own food cannot afford to throw anything away, because the nutrients locked inside its waste are the very nutrients its crops need to grow. To close the food loop, the colony must also close the waste loop, recovering the carbon, the nitrogen, and the minerals from everything its people and its plants discard, and feeding them back in to grow the next harvest. That means processing sewage into safe fertilizer, recapturing the carbon dioxide the crew breathes out so plants can breathe it in, and recycling the dead plant matter that food production leaves behind. It is the quiet machinery of a natural ecosystem. The endless recycling that Earth's soil and microbes and weather perform for free across the whole planet. Rebuilt from scratch inside a sealed room and run by equipment. And it carries a razor's edge of danger that the water and air loops share: contamination. A single failure in this recycling, a pathogen that slips through, a toxin that concentrates, a batch that spoils, can poison the food supply or the crew directly. The colony must become, in effect, its own soil, its own decomposers, and its own sanitation system all at once, closing every loop that Earth left open and keeping every one of them clean. So let us state this finding as plainly as everything before it. Local resources are real and valuable, and they can carry a settlement a meaningful distance away from total dependence. Water, oxygen, propellant, shielding, bulk metal, and well-sited power can all be won from the moon, and winning them would loosen the thread to Earth. But self-sufficiency is not a single thread. It is an entire fabric, woven from extraction, refining, manufacturing, electronics, chemistry, medicine, agriculture, and specialized repair, and the moon readily supplies only the coarsest of those. A colony that can mine its own oxygen and still must import every microchip, every medicine, every precision part, and every expert repair is a colony still bound to Earth at the level that matters most. It has moved from being supplied by Earth to being supplied a little less by Earth, and that is a real and worthy step. But it is not the same as being able to survive without Earth at all. The most local resources can do by themselves is turn a fully dependent base into a partially dependent one. The remaining dependence is the hard part, and mining does not touch it. And yet, imagine we push even this to its limit. Imagine a settlement generations from now that has somehow rebuilt a wide enough slice of the pyramid to forge its own alloys, print its own parts, brew a basic pharmacy, and grow its own food. Imagine it has done the near impossible and closed most of the industrial loop. Even that settlement, humming with local factories and green with local crops, would still face one demand that no furnace can meet, and no crop can fill, and no factory can print. It would still have to keep human bodies healthy. Not for a mission, but for a lifetime, and then for the lifetime of children born into that world, and their children after them, in a gravity 1/6 as strong as the one every human being who has ever lived has grown up inside. The moon can perhaps be made to yield its water, its air, its metal, and its power. Whether human biology can yield healthy people across whole generations in that feeble pool is a question no mining rig can answer, and it is the deepest uncertainty in the entire subject. That is where we go next. Imagine the settlement has won. Every argument from the earlier parts has, somehow, been answered. The air loops run clean, the scrubbers never fall behind, the water comes up reliably from the frozen crater, the reactor hums through the 2-week night, the regolith is heaped thick overhead against radiation and micrometeoroids, and against every odds we laid out earlier. A thin slice of local industry has begun to forge parts and grow food. Picture it thriving. Picture a real population, not a rotating crew of specialists, but families, people who have signed on to stay, greenhouses glowing, corridors busy, a place that by every visible measure looks like humanity has finally, permanently moved in. And now, picture the one thing that no amount of engineering in that scene has changed. The one condition that presses on every person there every second, waking and sleeping, and that no machine can switch off. Gravity. On the surface of the moon, the pull is roughly 1/6 of the pull you feel right now. Not zero. Not the near weightlessness of orbit. Something in between. A feeble, persistent tug. 1/6 of the force under which every human being who has ever been born grew up, aged, healed, and had children. And here we reach the deepest uncertainty in this entire subject, deeper than the dust, deeper than the machines, because it is the one place where we genuinely do not know the answer and cannot yet find it out. To understand why 1/6 gravity is such a menacing unknown, you have to understand something about the human body that is easy to forget. Your body is not a fixed structure that merely happens to sit inside Earth's gravity. Your body is in a constant, active conversation with that gravity. It is always listening to it, always measuring it, and always adjusting itself to match. Think of the body as keeping a running ledger with gravity, a continuous accounting of how much load it must bear, and quietly building or dismantling itself to fit the numbers in that ledger. Your bones are thick and strong not by accident, but because gravity demands it of them every day. And they maintain that strength only because the demand never stops. Your heart pumps against the weight of your own blood, which gravity is forever trying to pull in your legs, and it stays strong precisely because it works against that pull constantly. Take the pull away, or weaken it, and the ledger changes, and the body, efficient and unsentimental, begins to rebuild itself for the lighter world it now detects. We know this is true because we have watched it happen. Not on the moon, but in orbit, where astronauts live in near weightlessness aboard the International Space Station. And what we have learned there is sobering, though it is critical to say clearly that it comes from microgravity, from near zero pull, and not from the 1/6 pull of the moon. In microgravity, the body reads its ledger, sees that almost no load is required, and starts shedding what it now considers unnecessary. Bone that no longer bears weight demineralizes. Astronauts on long missions lose bone mass in the weight-bearing parts of their skeletons at a rate of very roughly 1 to 1.5% per month, month after month. A startling pace of quiet erosion. Muscles that no longer strain begin to waste. The heart and blood vessels, no longer fighting to push blood upward against weight, deondition, so that returning astronauts can struggle to stand without their blood pressure collapsing. Fluids that gravity normally pulls downward shift toward the head instead. And this shift is now strongly suspected to be behind a syndrome that reshapes the very structure of astronauts' eyes and degrades their vision, in some cases lastingly, a condition serious enough that it worries mission planners about journeys of long duration. The immune system itself appears to become dysregulated, behaving abnormally in ways researchers are still working to fully understand. And the whole body is simultaneously absorbing the radiation we described earlier, compounding every other stress. Now, against every one of those effects, the space station crews have a defense, and it is worth understanding what that defense actually is, because it exposes the trap. They exercise, relentlessly, Astronauts aboard the station spend something on the order of 2 hours every single day, strapped into specializer machines that force their bones and muscles to bear load artificially, manufacturing the very stress that gravity used to provide for free. It works. Partially. It slows the losses. It does not fully prevent them. But look closely at what that means. Even keeping a healthy adult body from deteriorating in low gravity is itself an active, powered, machine-dependent, time-consuming daily intervention. It is one more system that cannot stop, added to all the others. The body in low gravity joins the long list of things that must be continuously maintained by equipment, or it degrades. Human health on the moon is not a given. It is another loop that has to be run. And here is the crucial fork, the honest edge of what we know. All of that hard-won knowledge comes from microgravity, from bodies in near weightlessness. The moon is not near weightlessness. It offers 1/6 of Earth's pull, a real, persistent, downward force. And the staggering truth is that we have almost no idea what that partial gravity does to a human body over the long term, because no human being has ever lived in it for more than about 3 days. The Apollo crews touched it and left. Every long-duration data point we possess is from orbit, from zero, not from a sixth. So we are left with a question we cannot yet answer. Is 1/6 gravity enough load to keep the ledger honest? Enough to hold bone and muscle and heart and eye in healthy balance? Or is it so far below Earth's pull that the body still reads it as near absence and still begins the same slow disassembly, only more slowly? Or is there some threshold, somewhere between 0 and 1, above which the body stays healthy and below which it does not? And does 1/6 fall on the safe side of that line or the dangerous one? We do not know. We have never measured it. There is no partial gravity research station where humans have lived for years, and until there is, the effect of the moon's pull on a human lifetime is genuinely, honestly unknown. This is not a solved problem dressed up as mysterious. It is an actual void in human knowledge, sitting at the exact center of the colonization question. That uncertainty is already serious for the adults who would go. It becomes something far heavier when you consider who else a colony, by definition, must include. Because a base is staffed by adults who grew their bodies on Earth under full gravity and arrive already built. A colony is something else. A colony grows its own people. And that means, sooner or later, if the settlement is truly to be permanent and self-sustaining rather than a rotating outpost, it means pregnancy, birth, infancy, childhood, and the slow development of a human being from a single cell into an adult, all of it unfolding in 1/6 gravity. And of that, we know essentially nothing at all. Let us be extremely careful and extremely honest here, because this is precisely the kind of subject where speculation loves to outrun evidence. What is the actual state of knowledge? Human reproduction has never occurred beyond Earth. No human has ever been conceived, gestated, or born anywhere but on this planet, at full gravity. Our data on mammalian reproduction in space is limited and comes from animals, and even that data is thin and partial. Some experiments have shown fragments of the process working in altered gravity. Others hint at complications. Frozen mouse reproductive cells stored aboard the International Space Station, for instance, were later able to produce healthy offspring back on Earth, which is encouraging as far as it goes. But the full chain, conception, a pregnancy carried to term, a birth, and then an infant developing normally in space or in partial gravity has not been demonstrated even in mice, let alone in humans. We simply have not done it, and we cannot ethically leap straight to doing it with people. So every stage of building a new human is, on the moon, a question mark. Consider what full gravity does during development, because it does a great deal that we take entirely for granted. A developing fetus grows within fluid, and gravity shapes the mechanical environment of that growth. An infant learns to hold up its own head, then to sit, then to crawl, then to stand and walk, and every one of those milestones is a negotiation with gravity, the body calibrating itself against a pull it assumes will always be there. Bones lengthen and thicken according to the loads placed on them during childhood. The heart and circulatory system size themselves to the body they must serve under weight. The inner ear, the organ of balance, develops its sense of up and down in a world where down is defined by gravity. Grow a child in 1/6 of that pull, and you are not running a known process in a slightly different setting. You are running an experiment that has never been run on the most vulnerable possible subject, with no way to know in advance what a body calibrated from birth to 1/6 gravity would become. It might be fine. It might be subtly altered. It might be profoundly altered. We do not know, and the honesty of not knowing is the whole point. And this uncertainty coils back on itself in a way that is genuinely unsettling. One we are finally ready to sit with. Suppose children are born and raised in 1/6 gravity, and suppose their bodies calibrate themselves to it. Their bones and hearts and muscles built for a world 1/6 as heavy as the one their grandparents came from. What happens if such a person ever tries to come to Earth? A body that developed its entire structure under a feeble pull might find the full weight of Earth punishing, even dangerous, a gravity 6 times stronger than any its bones and heart ever prepared for. It is entirely speculative, and it must be labeled as speculative because no such person has ever existed, and no one can say with confidence what would happen. But the possibility is real enough to name. A settlement that raises its own children might, without ever intending to, produce human beings for whom Earth, the homeworld of the entire species, is no longer a place they can safely go. People native to the moon and exiled from Earth by their own biology, not by any wall or law, but by the quiet arithmetic of a body's lifelong ledger with gravity. Whether that would happen, we cannot say. That we cannot say is exactly what makes multi-generational settlement not a plan, but a gamble on questions we have not begun to answer. So now stand back and gather everything this story has laid out, because the point of assembling it all is to see that it was never a list of separate hazards. It was one problem, wearing many faces. We began with a world that provides nothing on its own. No air, no pressure, no drinkable water, no stable warmth, no shield, no forgiving margin. Then we saw that because the world provides nothing, everything must be manufactured and maintained by machines that can never fully stop, and that each of those machines is worn down by radiation, by micrometeoroids, and by the grinding dust, even as it runs, while the 2-week night starves it of power, and the choice between redundancy and launch mass leaves no comfortable answer. We saw next that the moon's own resources, water and oxygen and metal and shielding and well-sited power, can loosen the dependence on Earth, but cannot break it. Because self-sufficiency requires electronics and medicines and precision materials and an entire pyramid of tools that make tools, almost none of which a settlement can produce, so that repairing the colony may prove harder than building it was. And now we have seen that even a settlement that somehow solved all of that would still face a body that renegotiates itself with a weaker world, and a next generation whose development in that world is a complete unknown. Every one of those is a strand of a single rope, and the rope has a name. It is the dependency trap. And here at the end, we can finally state it in full. The moon threatens human life in dozens of ways, and the human answer to each threat is a system, a machine, an intervention. But every system built to hold back the moon is itself a thing that can fail and must be maintained. And nearly all of them still trace back, at their root, to Earth. To Earth-built electronics, and Earth-made medicines, and Earth-trained expertise, and Earth-shipped parts. And so the trap closes with terrible symmetry. The more thoroughly a settlement protects itself from a world that offers no natural support, the more machinery it must keep perfectly and endlessly alive. And the more machinery it must keep alive, the more ways it can die, and the more it must reach back to Earth to stay running. Protection breeds dependence. Dependence is the very thing a colony, by definition, must escape. This is why the problem is so severe, and why it does not yield to any single breakthrough. You cannot invent your way out of it with one clever machine, because every machine you add is another link in the chain you are trying to break. There is one more layer to this trap, and it is the most easily overlooked, because it is not made of metal or oxygen at all. It is knowledge. Everything we have described, the reactors and scrubbers and recyclers and extraction plants, depends not only on parts, but on people who understand them deeply enough to run them, diagnose them, and repair them when they fail in ways no manual predicted. On Earth, that understanding sits inside an immense, invisible reservoir. Millions of engineers, doctors, chemists, machinists, and technicians trained across decades in universities and apprenticeships and whole industries, so that for any broken thing there is always someone, somewhere, who knows how to fix it, and someone training the next generation to know it after them. A colony carries only a sliver of that reservoir, the handful of specialists it can fit aboard its ships. And knowledge, unlike metal, can vanish without anyone stealing it. If the one person in the settlement who truly understands the reactor dies, or the surgeon or the engineer who can coax the failing water plant back to life, their knowledge does not sit in a bin waiting to be reused. It is simply gone, unless it was taught in full to someone else in time. A colony meant to last for generations would therefore have to become its own university, as well as its own factory and hospital, preserving and passing down not just the tools of survival, but the deep expertise to wield them, generation after generation, with no room to lose a single essential craft. It is a library that must never lose a page, staffed by librarians who must never fail to train their replacements. And it is one more thing the moon does not provide, and Earth for a long time would have to keep supplying, in the form of trained human minds shipped up alongside the spare parts. And even knowledge fully preserved is not the end of what must be handed down. A colony that lasts must also pass on something harder to store in any manual: the will to stay. The first arrivals will be volunteers, chosen and driven, who cross space on purpose to be there. Their children will not have chosen it. They will simply have been born inside the machine, into a life of sealed corridors and rationed air and endless maintenance, on a world where a walk outside means a suit and a checklist and a mortal risk. A settlement meant to endure across generations must remain a place where people, generation after generation, still want to live and still agree to keep the machines running, governing themselves, resolving their conflicts, and shouldering the relentless work of survival, all without the vast web of societies and institutions that Earth uses to hold itself together. A colony is not only an engineering system and a biological one, it is a social one, and societies, like reactors, can fail. And this is where the deceptive closeness of the moon, the thing we began with, delivers its final and most subtle twist. Throughout this story, the moon's nearness has been quietly working on us, whispering that a world only 3 days away must surely be within our grasp. And in one specific important sense, that nearness is a genuine gift. The one real advantage the moon holds over every other destination. If something goes catastrophically wrong at a lunar settlement, a habitat breach, a reactor failure, a medical emergency, help from Earth is measured in days, and an evacuation home is at least conceivable. For a settlement on Mars, tens of millions of kilometers away, no rescue could arrive in time for almost anything. And a crew in crisis would be utterly, absolutely alone for many months. The moon is not like that. On the moon, rescue is plausible. And that plausibility is real, and it matters, and it will save lives. But look very carefully at what that gift actually is, because it hides the whole point inside itself. A settlement that can always be rescued from Earth is a settlement that still depends on Earth to survive its worst days. The rescue that makes the moon safer is the same rescue that proves the moon is not yet independent. Proximity does not loosen the trap. It disguises it. It lets a settlement remain profoundly dependent while feeling secure, because home is always just over the horizon, ready to catch it. And so the moon's closeness, which felt at the very beginning like the reason colonization would be easy, turns out to be the reason it is so easy to mistake occupation for independence. We could occupy the moon for a very long time, comfortably, precisely because Earth would always be close enough to fix our emergencies. And in doing so, we might never notice that we had built something that could not survive the day Earth stopped answering. Which brings us at last to the question everything so far has been walking toward. What actually turns a base into a colony? When does occupation become independence? It is worth being precise, because the obvious answers are all wrong, and their wrongness is the whole lesson. It is not the first landing. The Apollo crews landed and left, and nothing was colonized. It is not the first permanent habitat, because a habitat is only a shelter supplied from home. It is not the first crew that stays for a year, because a year of resupply is still a year of dependence. It is not even the first breath of oxygen mined from lunar soil, or the first cup of water pulled from a frozen crater, or the first part printed from local metal, because all of those, wondrous as they are, only move the settlement from fully dependent to slightly less dependent. None of these milestones, however much they would be celebrated, is the moment of birth. The real moment, the only one that counts, is quieter and far more frightening. A base becomes a colony the first time it suffers a major failure, a genuine disaster, the kind of blow that would ordinarily demand rescue from home, and survives it alone by its own resources because it could repair itself, replace what broke, treat its own wounded, and keep its people alive and healthy without Earth having to save it. That is the threshold. Not a triumph, but a survived catastrophe. Not a ribbon cut on a new habitat, but a night when everything went wrong and the settlement on its own made it to morning. It is worth making that threshold concrete, because it is easy to say and hard to truly picture. Imagine the reactor faults in the depth of the 2-week night. Its steady power gone. The cold beginning to seep inward while the batteries drain and the heaters fight a losing battle. Imagine, in the same stretch, a seal fails somewhere and the pressure begins its slow bleed into the dark. And a crew member is badly hurt in the scramble to respond, needing surgery and medicines that cannot be reordered. On a base, this is the moment the call goes out to Earth, and the only question is whether rescue arrives in time. On a true colony, there is no such call, because the settlement can restart or replace its own power, seal its own breach with parts it made itself, and treat its own wounded with a surgeon and a pharmacy it already holds within its walls. It looks the disaster in the face and it answers, alone. That is the birth we are talking about. A night the settlement survived from within. The Earth never even had to hear about until it was already over. Until a lunar settlement has crossed that line, it has not become a new world. No matter how many people it holds or how established it looks, it has only extended the old one. And so we return finally to the potted plant. A plant in a pot can look thriving for years. It can grow tall and green and flower and seem, to any casual eye, thoroughly alive and thoroughly established. But it has no roots in the ground. It is alive only because someone is watering it. And the day the watering stops, it dies, no matter how established it looked the day before. A base on the moon, however large, however busy, however permanent it appears, is a potted plant. Its greenness is real, but its roots are not in the moon. Its roots run all the way back to Earth, through every microchip and every medicine and every rescue that stands ready over the horizon. A colony, a true one, would be a plant with roots in the ground it grows in, able to survive when no one comes to water it. And the horrifying problem, stated one last time and in full, is this. The distance between the potted plant and the rooted one is not a distance of engineering skill or national will or funding or time. It is the distance between keeping people alive inside an artificial world and recreating enough of Earth's entire biological and industrial foundation that the artificial world could stand on its own on a moon that offers no natural support of any kind, with a human biology we have never tested across a single generation, let alone many. We will almost certainly return to the moon. We will very likely stay for a while, then longer, then perhaps continuously. We will land and build and mine, and one day watch a settlement grow busy enough that headlines will announce that humanity has colonized another world. And on the day that announcement is made, it will be worth remembering the difference we have tried to draw tonight, because a settlement can look like a new civilization long before it becomes one. The first lunar city may glitter under the black sky, and hold a thriving population, and produce its own oxygen and print its own parts, and still be, at its foundation, a fragile extension of Earth, kept alive by a supply line and a rescue promise, standing on a world where every natural condition remains quietly, permanently hostile to its existence. It will have crossed enormous distances to get there. The last distance, the one between occupying the moon and belonging to it, between being kept alive by home and being able to live without it, is the one that matters, and it is the one no rocket can cross for us. It will only be crossed the first time the settlement faces the loss of everything, and does not call home because it does not have to. That is the horrifying problem with colonizing the moon. Not that we cannot reach it, not that we cannot survive there, but that survival and colonization were never the same thing, and the closeness that makes the moon feel like ours is the very thing that will let us forget the difference. right up until the day, the difference is all that is left.